ever feel totally swamped by choices? Like maybe planning a vacation with just, I don't know, tons of places you could go and things you could do, or even just scrolling through Netflix forever.
Oh, yeah, that feeling. Choice paralysis, right?
Yeah.
It's actually a pretty good way to think about a big challenge in software testing.
How so?
Well, imagine you've got this complex piece of software, loads of interacting parts. How do you actually test it thoroughly without getting completely lost in like an infinite number of ways things could go wrong?
Okay, yeah, I see that. So you could test forever and still miss something.
Exactly. And well, that's where something called orthogonal array testing, or OAT, comes into the picture.
OAT, yeah.
Yeah. Instead of trying absolutely everything, which is often just impossible, OAT is a smarter way. It's based on statistics, helps you explore the system, get a really good feel for it, but with way less effort.
Sort of like a shortcut to understanding.
Kind of, yeah. An express lane, maybe? So our plan today is to really dig into what OAT is, why it's so useful, especially for software with lots of inputs and settings, and how it manages to be efficient but still catch the important stuff.
All right. And we're looking at some explanations of OAT to help us out.
Yep, some straightforward sources explaining the core ideas.
Okay, so this OAT thing, what's the basic principle? What makes it different from just, randomly picking some tests?
Right. So at its heart, OAT uses these mathematical structures called orthogonal arrays. Think of them as pre-designed templates for creating test cases.
Orthogonal arrays.
Oh, okay. Yeah, it sounds fancy, but the idea is statistical. It's really valuable when you're dealing with systems that have like tons of different data inputs you could throw at them.
So it's not just guesswork or testing one thing at a time. It's more strategic than that.
Absolutely. The real kicker isn't just fewer tests, though that's great. It's why you can use fewer tests. See, a huge chunk of software bugs, they actually pop up because of how just two things interact, two variables.
Ah, okay. Not some crazy five-way interaction usually.
Right. Usually not. OAT is specifically designed to hit those critical two-way interactions. That's what makes it so efficient at finding the most probable issues. It intelligently pairs up and combines the inputs.
So you get good coverage with fewer tests, which means less time spent testing.
Exactly. Saves time, saves resources. It's about maximizing that coverage smartly.
Gotcha. The source material mentioned an example, something about train tickets. Can you maybe walk through that? It might make the pairing idea clearer.
Sure thing. So imagine you're testing the system that verifies train tickets, right? You've got a few different factors to consider,
Right.
like how many people are on the ticket, the actual ticket number, the seat numbers, the train number, stuff like that.
Okay.
Now, if you just tested each thing on its own or just mix them up randomly, you could easily miss a bug that only happens when, say, a specific seat number is used on a particular train line.
Right, like maybe seat 12A on the express train always causes an error no matter who's traveling.
Exactly that kind of thing. Now, if you tried to test every single possible combination of passengers, ticket numbers, seats, trains, oh man, the number of tests would be astronomical, just huge.
Yeah, I can imagine.
So OAT and this related idea of pairwise testing they mention, it takes a different approach. It focuses on making sure that every possible pair of values gets tested together at least once.
Every pair.
Yeah. So every combination of, say, number of passengers and train number gets tested, and every combo of seat number and ticket number and so on for all the pairs.
Okay.
Think of it like if your car won't start, it's probably battery, or maybe you're out of gas, right? It's less likely to be some super specific combination of like low tire pressure, the radio volume being at 7 and it being Tuesday. Software bugs often work like that most, are triggered by just two things interacting badly.
Okay, that makes sense. It's about those key relationships between settings, not every single possibility under the sun. So why is this particularly important for, software development?
Well, the source hits this point hard. Making good software is just getting trickier because the code itself is so complex now. Think about modern apps. You've got user settings, connections to other services, mobile, web. And it's not like the old days with just a few simple inputs. It's a really tangled web sometimes.
Yeah, definitely feels that way. You change one tiny thing over here and something totally unexpected breaks over there.
Precisely. So that old idea of trying to test every single combination, that n number of test cases the source talks about, it just explodes. It becomes completely impractical.
Yeah.
And testers, they're always under pressure, right? Tight deadlines, user feedback coming in, documentation changing. They just don't have infinite time to run every conceivable test.
So you've got limited time, limited resources. You got to be smart about it.
Exactly. That's where this idea of test case optimization fits in. The goal is, how do we get the most bang for our testing buck? Maximum coverage, minimum effort.
And OAT is a way to do that optimization.
Yes, it gives you a systematic statistical way to do it, and it zeroes in on those pairwise interactions, which, like the source says, are often where the really nasty, hard-to-find bugs like to hide, especially where different parts of the system connect the integration points.
Okay, this is interesting. So OAT isn't necessarily going to find every single obscure 1 in a million bug.
Right, probably not.
But it's really good at finding the majority of problems because it focuses on how pairs of things work together.
That's the key trade-off, yeah. It might miss a bug that only happens when 3 or 4 specific things line up just so. But it's incredibly effective at catching bugs caused by setting A messing with setting B. And the beauty of the orthogonal part is that it mathematically guarantees that every pair of variables gets tested across all their possible values.
Guaranteed pairwise coverage.
Okay.
So how does this OAT magic actually get set up? Is there a formula or something?
Yeah, there's a kind of standard way to write it down. A notation, it looks like L, then a subscript N, then in parentheses V raised to the power of KL sub jami V sub P sub.
L and VK. Okay, looks a bit like algebra. Let's break that down.
Yeah, let's decode it. So the N, that's the number of runs. Each run is basically a row in this special table, the orthogonal array. And each row turns directly into one test case you need to run.
Okay, so N is the number of tests we end up doing. Simple enough. What about K?
K is the number of factors. Think of factors as the columns in that table. They represent the different variables or inputs you're testing, the maximum number the array can handle.
So if I'm testing, say, 5 different user settings, my K would be 5.
Exactly. Yep. And finally, V stands for levels. That's the maximum number of different options or values any one of your factors can have.
Ah, right. Like if a setting is on or off, that's 2 levels. If another's low, medium, high, that's 3 levels.
Precisely. So the source mentions you look at all your factors, find the one with the most options, and that number sets your V. So that L sub and sub V sub K sub thing is just a compact way to describe the structure of the test set you're using.
Got it. So N tests for K variables, where each variable has up to V options. A shorthand guide.
You got it. It summarizes the design.
Okay, so we understand the what and why a bit better now. How do you actually do it, like practically? The source gave some steps and examples.
Yeah, it lays out a pretty logical flow. First, you got to really pin down the independent variables, the inputs, the settings you want to test.
Step 1, know what you're testing. Makes sense.
Step 2, you find the right orthogonal array, the smallest one that fits your number of factors, K and levels, V. Often you actually look these up in standard tables. The source mentions finding one with the right number of runs, N.
So these orthogonal arrays, they're like pre-built templates.
Kind of, yeah. Decades of statistical work went into making them. They're designed so the combinations are spread out evenly, covering those pairs without being redundant. Orthogonal just means independent or non-overlapping in a specific mathematical way.
Okay, so you pick your template, then what?
Then, step 3, you map your actual factors, your variables, onto the columns of that array template. Step 4, you take the values each variable can have, like on, off, or low, medium, high, and assign them to the levels shown in the array.
Right, so you're filling in the template with your specific stuff.
Exactly. And finally, step 5, each completed row, each run in the array, becomes a concrete test case you need to execute. Oh, and the source adds a good point. Sometimes you might want to toss in a few extra tests manually if you have a gut feeling about a risky combination that the array didn't happen to generate.
Right, cover your bases if something feels suspicious. Okay, seems structured. Let's look at that first example, the web page sections.
Okay, so scenario is a web page with 3 sections, top, middle, bottom. Each one can be either hidden or shown.
3 things, each with 2 options.
Yeah, so 3 factors, K3, and 2 levels for each, V2. The source says this points to an array called L sub 4 sub 2 sub 3 sub. The 4 tells us we need 4 tests.
And normally, testing every combo would be 2 times 2 times 2. 8 tests, right? To see every possible hidden shown mix across all 3 sections.
Exactly right. 8 tests for the exhaustive approach. But using this L sub 4 subarray, you only need those 4 specific combinations.
Wow, half the tests. And the source showed a little table with those 4.
Yeah, it clearly laid out which sections are hidden and which are visible in each of the 4 tests. It's pretty neat how it guarantees every pair of sections. Top, middle, bottom, middle, bottom. Gets tested in both hidden, 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 visible, visible, hidden, and visible, visible combinations within those 4 tests.
That's efficient. Okay, what are the second example? The microprocessor one. That sounded more complex.
Yeah, a bit more involved. Here we had 4 factors: temperature, pressure, doping amount, and deposition rate.
And each one had 3 settings, 3 levels.
That's it. Temp could be 100, 150, or 200 degrees. Pressure, 2, 5, or 8 psi, and so on. 3 levels for each of the 4 factors.
So the old way, testing every combo. That would be 3 times 3 times 3 times 3.
Which comes out to 81 test cases.
81. Wow, that's a lot of testing.
It really is. Now, applying OAT here, you've got 4 factors, K4, and 3 levels, V3. The source shows the start of building the array and L sub 9 sub 3 sub 4, It doesn't list all 9 rows, but it gives the idea, the main point. Instead of 81 tests, you only need 9. 9 test cases using that specific orthogonal array.
9. Down from 81. That is a massive reduction.
Huge. And you're still getting that systematic coverage of all the pairwise interactions between temperature and pressure, temperature and doping, pressure and deposition rate, et cetera, et cetera.
Yeah, that really drives home the efficiency point, especially when things get more complicated.
Definitely illustrates the power when you have multiple variables with multiple options.
Okay, so summing up then, what are the big advantages of using OAT?
Well, the source lists several key ones. Number 1, top of the list. It guarantees you test all the pairwise combinations of the factors you chose. That's huge.
Guaranteed pairs. Got it.
Second, as we just saw, it massively reduces the number of test cases you need to run. Dramatically sometimes.
Fewer tests. Yeah.
Which, third, lets you tackle testing complex situations with lots of variables much more efficiently. Fourth, generating the tests using an array is often simpler and less prone to human error than trying to invent a comprehensive set by hand.
Easier to create the test, too.
Yeah. Fifth, the source highlights it's really useful for integration testing, checking how different modules or components work together.
Good for integration. Okay.
And finally, all that adds up to better productivity. You get through test cycles faster, spend less time overall on this phase of testing.
Those are some pretty strong arguments for it. But it can't be perfect, right? Are there downsides or maybe common mistakes people make?
Yeah, the source brings up some important caveats. One thing is, if you have a really huge number of inputs, even with OAT, managing the tests can still get pretty complex. You might need test automation tools to help run them and track results.
So complexity can still be a factor if it's big enough.
Right, and it also repeats that OAT is particularly good for that integration testing piece.
Okay. And what about mistakes? Things to watch out for.
The source mentions a few traps, like maybe not understanding the system well enough, so you end up focusing your OAT effort on the wrong things, the less risky parts.
Ah, so you need to pick the right factors to test.
Exactly. Picking the wrong parameters to combine is another mistake. You need to choose the ones most likely to interact badly. Also, using OAT when you only need very basic testing, it can be overkill for really simple stuff.
Don't use a sledgehammer to crack a nut.
Pretty much. And finally, it warns about trying to apply OAT manually if the application is super high risk. For critical systems, the potential for human error in setting it up might mean you're better off with automated tools and maybe more rigorous methods on top.
Okay, so it's a powerful tool, but you need to apply it thoughtfully in the right context.
Precisely. It's not, a magic bullet that replaces all other testing, but it's a very, very effective technique for getting broad interaction coverage with a manageable set of tests.
All right, so let's try and wrap this up. We've basically learned that orthogonal array testing, OAT, is this really smart, strategic way to approach testing, especially when you've got tons of settings or inputs interacting.
Yeah, instead of drowning in possibilities, trying to test every single one.
Which is often impossible anyway.
Right. OAT lets you focus and make sure all the important pairs of inputs get tested together.
And the big benefit for, anyone listening trying to get their head around complex system software or otherwise is that you can get a really solid understanding of how things interact with way less effort than exhaustive testing.
Exactly. It's about efficient exploration, getting the most insight for your testing time.
That brings up a kind of interesting thought, this whole idea of focusing on the key interactions, the pairwise stuff.
Yeah.
I wonder how much that principle could apply elsewhere.
How do you mean?
Like outside of software. If you're dealing with complexity in, analyzing customer feedback with lots of variables, or market trends, or even just troubleshooting some complicated problem in your own life, could you use a similar kind of strategic sampling? Focus on the key pairings.
Huh. That's a really great question. It makes you think, doesn't it? Because fundamentally, it is about a structured way to tackle complexity. Understanding a technique like OAT in one area, yeah, maybe the underlying principle of checking key interactions strategically. Maybe that gives you a more confident, more efficient way to approach complex information and systems pretty much anywhere.
Food for thought, definitely. It's about smarter exploration.
Exactly, being strategic about where you put your effort to understand things.
CTSS Academy Podcast, where ideas ignite and futures form.